So here we are, topic 6, international equity and commodity portfolios. So lecture notes, here we are. And we're going to be covering the single index model and a bit of background on regression, just to refresh you about regression analysis. And then simple historical and normal VAR with one equity risk factor, then equity VAR with multiple risk factors, and then we bring in the FX rates, and then we look at commodity portfolios. So those are the 5 parts. And let's start now with the single index model. And remind ourselves what we're looking at in this video is equity risk, which is the uncertainty in the market value of a portfolio due to changes in equity risk factors. So a stock portfolio could have, as well as equity risk, foreign exchange risk, or also called currency risk, because it may be that you have foreign stocks in your portfolio. So equity risk wouldn't be the only risk. At the beginning, we're just going to be looking at domestic stocks. And so the only risk factors are equity risk factors. And we're not going to be looking at options, only linear equity portfolios. So these are a collection of shares. We can write the portfolio return as the weighted sum of the asset returns, or equity futures, or exchange traded funds, also called ETFs. And all these portfolios have a risk factor mapping that is linear. It's based on linear regression. So we can use the normal VAR model, which applies to linear portfolios, and the historical VAR model, which applies to any type of portfolio. But we're not going to use Monte Carlo, because we'd only use that if we'd have some very weird distributions, because we can get formulae, not just normal formula, we can get the T distribution VAR formula, we can have a normal mixture distribution VAR formula. So these are generally enough. Don't need Monte Carlo. So who is affected by equity risk? Well, companies that issue the shares, of course, they generally keep most of the shares themselves, so they're going to be subject to equity risk. Any investors in stock markets or other equity markets like equity futures or exchange traded funds. That's mainly asset managers, hedge funds, of course. Pension funds are large investors in equity markets, and corporate treasury. So the portfolios can have long, i.e. buy positions, or short, that's a sell position. And a short position in a share is achieved using something called repo. It's a short sell. In other words, you sell something, but you're short it. In other words, you don't have it, you have to borrow it. So a typical example of repo is, say, I sell when I think the price is going to go down, otherwise I'd buy, right? So I think the price of iPhone 16s, or whatever model it is at the moment, I know that there's going to be a new iPhone announcement, and so the latest model is going to decrease in price when the announcement's made, but that's my private knowledge, and I'm fairly sure the price is going to go down. So, and I don't have an iPhone, so I say to my friend, can I borrow your iPhone? And it's like, it looks like this, and so I say, I'm going to give you $10 if I can just borrow your iPhone for 24 hours, or $100, or whatever somebody wants. Okay, give them some money to borrow, and then you wipe it and save it on the cloud, and then you sell this iPhone, and the next day, lo and behold, the price has gone down $300 or whatever, and you buy it back. Well, if not that one, a very similar one, which you then reinstall all the settings, and your friend doesn't know it's a different phone. Well, maybe that's not exactly how repo works, but that gives you the idea, is that you borrow something, you pay somebody to borrow it, and then you sell it, and then buy it back once the price has fallen. If it has fallen, you better be right when you repo. So what are risk factors for equity portfolios? Well, just in the single index model we're going to be talking about in this section, we just have a general market risk factor. A broad, big index like S&P 500, that's for US stocks. The FTSE 100 is probably the biggest for the UK stocks. Of course, there are fewer stocks, but these are, the largest cap stocks. And if it's a domestic portfolio, you could just have that single risk factor and that would be it. And that's what we cover in the one factor VAR model in the next section. But in section 3, we consider using sector indices like a pharmaceutical index or an agricultural stock index, or different types of stocks. So that allows us to disaggregate risk, to attribute it to more granular level risk drivers. And then in section 4, we show that equity portfolios that include foreign stocks must also have the relevant exchange rates as risk factors. So the risk factor mapping for equity portfolios is based on regression. And just recall what regression is. You've got at least one, maybe more, X variables. These are the right-hand side independent variables. And on the left-hand side, you've got your one dependent variable. That's what you're trying to explain. And we use this simple linear model, SLM, which is with one explanatory variable. Here, if we've just got a broad market index. So we express y as a linear function of x, and then we add this error term, which is IID, and because it's an error, it must have zero expectation, and it has some variance, sigma squared, and we use some data, some time series data from t equals 1 to some other long time, t years of data maybe, or a few months of data. And given that data, we can draw a scatter plot of x and y, and it's not a perfect line because y is stochastic. We can't really predict y. That's what the error term, this stochastic variable with a distribution, gives the distribution of y. X could be deterministic, but usually isn't. So this is the line of best fit if we ignore the epsilon, the error term, and including that, we can explain every single point. And what we're interested in for risk factor mapping is this beta. This is the effect of x on y. It's the change in y per unit change in x. So you have to think of the units of measurement. If x is in percent, then y, it's the beta measures the change in y in percent if x increases by 1%. And it's only if beta is 0 that x has no effect on y. So we can look at particular observations. So instead of the model, which has capital letters here for these random variables y and x, not for the epsilon, but when we get particular observations, we have a sample. We've got x1 and y1, x2 and y2, x3 and y3, and those are the crosses you can see in this diagram. So there are 100 or so crosses in that diagram. So we have a sample xt, yt, t equals 1 till 100. And a residual is an observation on this error process, epsilon. It's the difference between the actual and the fitted values of y at time t. So, for example, this residual here, as negative residual, is the actual y is just above 0. The fitted y is the red line, and that's value is like 11 or 12, and so the residual is about 1 minus 11, so it's something like minus 10 in this case. And now we put hats on alpha and beta because they are the estimated intercept. Alpha is where it cuts, the line cuts the vertical axis, that's the intercept, and the beta is the slope of the line. And then just to review ordinary least squares, when we've got data on these random variables, we estimate the model parameters by minimizing the residual sum of squares. That's RSS, which is, this is the sum of the residuals squared on the right-hand side. And we don't minimize the sum of the residuals because we could have some very large negative residuals like this one here, balanced by some large positive residuals. And in fact, that red line could just as easily slope downwards and the sum of the residuals could be 0. But it's the sum of the squared residuals that we minimize. And if we do that, a little bit of algebra shows that the formula, that the beta hat is the sample covariance between x and y divided by the sample variance of x. And then y is just, and then alpha hat is just the mean of y minus beta hat times the mean of the sample x. And sigma hat is the standard error of the regression. That's the residual sum of squares divided by t minus 2, not t minus 1. Why is that? Well, in order to compute each residual, we have to know alpha hat and beta hat. So we've lost 2 degrees of freedom. We have to first calculate beta hat, then knowing beta hat, we can calculate alpha hat, and only then can we calculate sigma hat. So that's why we divide by t minus 2, not t minus k. And in general, if you've got k betas, k explanatory variables, then you would take off k plus 1, 1 for the constant as well. Now, you don't actually have to do regression to get the simple beta, because this formula here, sxy over sx squared, can be written, well, the covariance is, if you remember, the correlation times the product of the 2 standard deviations. And then when you divide that by sx squared, you can cancel 1sx, and that leaves the correlation times sy over sx. Sy over sx is called the relative volatility of y and x. And y is typically a stock or a stock portfolio. X is a broad market index. So x is not going to be as variable as y, which means that usually the relative volatility is bigger than 1. And so the beta hat is bigger than the correlation. Correlation, of course, is bounded between -1 and 1, but that isn't necessarily the case. Beta could be, so correlation is 0.5, beta could very easily be 2. Beta will always have the same sign as the correlation, though. Single index model is when y and x are the returns, or P&L, on the stock or a stock portfolio and a broad equity market index. So that's why we call the simple linear model SLM, which is y equals alpha plus beta xt plus epsilon t. We call it the single index model when we have those particular variables. And here's an example where the x variable is the broad market index, that's the S&P 100, and the y is a single stock, that's Amex. And here I've drawn a scatter plot of the returns, which are sometimes positive. The center is around 0. Amex one day returned over 6% when the S&P 500 returned less than 1%. Alternatively, you've got negative returns, and sometimes you have negative returns on Amex when the S&P return is positive. Those are the dots underneath the right-hand side of the line of best fit, the regression line. Okay, so we can calculate a beta using this formula without even having to do regression. That's not the case in the multiple linear regression. We don't have simple formulae in that case, but in this particular case, for the single index model, we do. And we can then express it either as percentage or nominal terms. So if we're doing a regression on returns, we'll get percentage beta. If we do regression on P&L, we'll get a nominal beta. But we can go from one to the other, so we can convert, for example, a percentage beta to a nominal beta by multiplying by the current stock or portfolio price. So, for example, a fund's got 10 million in UK stocks, 5 million in US stocks, and 3 million in European stocks. And suppose the percentage betas for each of those, so relative to, say, the FTSE 100, the beta is 1.2. Relative to the S&P 500, the beta is 1.5, and relative to the Euro Stoxx 50, the beta is 2. So those are the percentage betas. And nominal betas, you have to multiply the amount the fund invests in those markets. So taking 1.2 times 10 million for the UK gives 12 million pounds for the nominal beta, and likewise for the other two. We just multiply the pound sterling 5 million or 3 million times the percentage betas to get the nominal betas all in sterling terms. And if we've got stock betas, we can convert them into a portfolio beta as long as we know the weights in the portfolio. So all the betas have got to be respect to the same equity risk factor in this portfolio, okay? Not as in the previous example where we had 3 different equity risk factors. I was just illustrating how to convert percentage to nominal. Here we're talking about one equity risk factor, but you've got different stock betas, and you want to find the beta of the portfolio. And so you can get each individual stock beta using this single index model, or using this here. And then when you've got the stock betas, you just take the weighted sum of all the stock betas to get the portfolio beta, which I've called here beta P. For example, suppose your weights are 25% and 75%, and the percentage betas are 0.8 and 0.2, then the percentage portfolio beta is going to be 0.25 times 0.8 plus 0.75 times 0.2, which is 1.7. And so, for example, if the portfolio value is $5 million, the nominal beta is just 5 million times that. As always, there's lots of different orders you can do the calculations. If you want, you could take the nominal betas straight away. So we've got percentage betas of 0.8 and 2. We could multiply 0.8 times 5 to get 4 million, and 2 times 5 to get 10 million. And then we just use the weighted sum of the nominal betas. So this red formula here on this slide applies whether the betas are percentage or nominal. So that's it for this video. See you in the next one.